In this video, I'm going to show you how to work out this problem, which has to do with steady-state flow to wells in a confined aquifer. The question is, a productive well pumps water from a confined aquifer at a constant rate of 25.0 liters per second. The drawdown in two piezometers located 30.0 meters and 40.0 meters apart from the well are 4.0 meters and 2.0 meters respectively. Assuming the aquifer to be 35.0 meters deep. Number 1. Illustrate the information with the aid of a diagram. 2. Calculate the transmissivity of the aquifer. 3. Determine the storativity of the aquifer. So without further ado, let's begin with question number 1 and illustrate the information with the aid of a diagram. This is the diagram. As you can see, we have three wells. We have the test well or the main well. We also have observation well 1 and observation well 2. The observation wells are known as piezometers. GL stands for ground level or the ground surface. The red dashed line represents the initial steady water table. The little inverted triangle stands for free surface of the water or water table. As water is being withdrawn from the test well, it results to the formation of cone of depression. So R, which is the radius of influence, is the maximum distance from the test well at which the effect of pumping is being felt or are being felt. So we have R1 and R2. Also S stands for the drawdown. We have X1 for observation well 1 and S2 for observation well 2. The drawdown is the difference between the initial steady water table and the pumping water level. We also have these arrows here, which represent the radial flow of water in the aquifer towards the test well. B stands for the thickness of the aquifer. So the next question, which is question number 2, calculate the transmissivity of the aquifer. To find the transmissivity, we're going to use Tim's equation for steady-state flow to wells in confined aquifer. The equation is given as recall that ln of x equals 2.303 log base 10 of x. So we're going to substitute this into the formula. And also we're going to set H2 and H1 as x1 and S2. The reason is because we are given the values for x, which is the drawdown. We are not given the values for h in the equation. So let's substitute it into the formula. Let's rearrange the formula. This is the formula we're going to use to calculate the transmissivity. Now let's go back to the question. In the question, we are given Q, which is the discharge, as 25.0 liter per second. We are also given the radius of influence, which is R, as 30.0 meters for R1 and 40.0 meters for R2. The drawdown, which is S, is given as 4.0 meters, which is X1, and 2.0 meters, which is S2. The thickness of the aquifer is given as 35.0 meters, which is B. Now, as you can see, all our values are given to us in meters, except the discharge, which is 25.0 liters per second. So we have to convert it to either cubic meters per hour or cubic meters per day, so that we will have uniform units. So if you want your final answer to be in square meters per hour, then you convert it to cubic meters per hour. Or if you want your answer to be in, that's your final answer to be in square meters per day, then convert 25 to cubic meters per day. So in this case, I'm going to convert the discharge to cubic meters per hour so that our final answer will be in square meters per hour. So now let's multiply 25 by 3600 and divide it by 1000. So we have 90 cubic meters per hour. So now that we have the conversion for the Q value in cubic meters per hour, let's substitute the values into the formula and find the transmissivity. So we have T equals Q, which is 90 cubic meters per hour times 2.303 log base 10 of 40, which is the R2, over 30, which is the R1, divided by 2 pi 4 minus 2. So this unit will cancel this, and also this will cancel one of these to give us a square meter. So we have 90 square meters per hour times 2.303 log base 10. So if we divide 40 by 30, we have 1.333, a recurring decimal, over 2 times 3.142. Remember that pi is equal to 3.142 times 2. Now let's find the log of 1.333. Log of 1.3333 is 0.124938, so on. So we have 90 square meters per hour times 2.303 times 0.1249. 2 times 3.142 times 2. We have 12.56. Now let's multiply 90 by 2.303 and 0.1249. We have 25.88823 divided by 12.56. So let's divide it by 12.56. We have the final answer as 2.061 square meters per hour. This is the answer in square meters per hour. To get an answer in square meters per day, we can convert these to square meter per day. So let's convert this to square meter per day. So we have 49.46. 49.4 47. Let's approximate it. So we have 47 square meters per day. This is the answer in square meters per day. So that is it for question number 2. Next, we're going to determine the storativity of the aquifer. So question number 3. The storativity of an aquifer can be determined by multiplying the specific storage, which is x subscript x, by the thickness of the aquifer. However, we are not given the value for specific storage in the equation. So how are we going to find the storativity? Well, according to Lohmann, the storativity of a confined aquifer can be approximated or estimated as so B is the thickness of the aquifer. So from the equation, we know the value of B, which is given to us as 35. So let's put in the value into this formula to get the storativity. So we have 0.0000033 meters times 35.0 meters. So this unit will cancel this unit. So if you multiply 0.000005033 times 35, we have 0.00000 0.0001155. Zero point zero 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 1155. This is the storativity of the aquifer.